Hi, in this video I'm going to prove the Weierstrass approximation theorem using a constructive way. And first of all, I will define what a Bernstein polynomial is. Well, the n plus 1 Bernstein basis polynomials of degree n are defined as bvnx equal to ncv times x to the power v times 1 minus x to the power n minus v, where v runs from 0 to n. And a linear combination of the Bernstein basis polynomials b and x is called a Bernstein polynomial, or a polynomial in Bernstein form of degree n. We should notice something. We should know that the sum of all degree n Bernstein basis polynomial is equal to 1, and this is the consequence of the binomial theorem. Second, we should know that the Bernstein polynomial themselves are bigger than or equal to 1. It is because I restricted the t between 1 and 0. And let's suppose that f is a continuous function over the closed interval 0 to 1. Let's define the nth Bernstein polynomial of f to be the summation from k equal to 0 up to m of f k over n times b, k, and t. And we denote this expression to be b n t f. And this notation means the Bernstein polynomial of degree n of f at the point t. So the difference between f and its nth Bernstein polynomial can be written in this form. Well, you may wonder why we can write it in this form. And this is because as the t is independent of the index here, we can factor it out and get the summation from k equal to 0 up to n. And remember that from the above, we know that the summation from k equal to 0 up to n of b, k, and t is equal to 1. So this is essentially ft times 1, and this is equal to ft. So next, we factor out b, k, and t from both expressions, and we get the second line here. Remember that the Weierstrass approximation theorem states that if f is a continuous function over the closed interval, then we know that it can be uniformly approximated by a polynomial. And that means for all epsilon greater than 0, there exists a polynomial p such that the subnorm of the difference between f and that polynomial is more than epsilon. Therefore, we should consider the subnorm. Well, first of all, let's recall that f is a continuous function on a compact set, means that it is uniformly continuous on this interval. And that means for all epsilon greater than 0, there is a delta greater than 0 such that as the absolute value of x minus y is smaller than delta, then the absolute value of fx minus fy is smaller than epsilon for all xy inside the interval 0 to 1. Well, to approximate our supremum, we will divide our terms into two parts. The first part is a integer k between 0 and n such that the absolute value of t minus k over n is smaller than delta. And the second part is the integer k between 0 to an n such that the absolute value of t minus k over n is greater than or equal to delta. And therefore, the union of these two sets will give all the integers from 1 to n. Therefore, if we have divided our integer into two parts, then we can approximate it individually. And using the triangle inequality and the approximation above, we know that whenever the difference between t and k over n is smaller than delta, then the difference between fk over n and ft is smaller than epsilon. Therefore, we have the term epsilon here. And the remaining term is the subnorm of the summation of b, k, and t, where k lies inside the first set here. And the second term is essentially the terms inside this second set. We know that the Bernstein polynomial are non-negative. Therefore, we can make it even bigger by adding all the Bernstein basis polynomial from 1 to n. And this gives rise to a factor of 1. Therefore, we're left with the term epsilon here. And second, we know that f is a continuous function over a closed interval, so by the extreme value theorem, we know that its maximum exists. Therefore, this term here can be approximated by 2 times the sup of f inside the interval 0 to 1. And therefore, we are left with the term 2 times the supremum of f times the supremum of such expression. However, if this term here is not small enough, then we cannot finish approximation. So here is the trick to approximate this expression. And remember that when k lies inside the second set here, then the absolute value of the difference between t and k over n is greater than or equal to delta. So if we take square to both sides, we get this expression. So we know that if we divide the delta square to the left hand side, we get that the quotient is greater than or equal to 1. So using this fact, we know that this expression here can be approximated by this expression, because this thing over delta square is greater than 0. And by expanding this expression, we get the following. And notice that t squared times b, k, and t is essentially the Bernstein polynomial of 1 at t times t squared. And this expression here is essentially 2t times the Bernstein polynomial of t at t, because it is t over n times b, k, and t. The third expression here, we know that it is k over n squared, and therefore k over n squared times b, k, and t is essentially the Bernstein polynomial of t squared as t. And we would like to directly compute these bnt1, bntt, and bntt squared. Well, you may wonder, how can we do so? First of all, we evoke the binomial theorem. The n squared of t plus y is equal to the summation from k equal to 0 up to n of n ck tk y to the n minus k. So if we differentiate both sides and make some rearrangement, we will get the second line here. And if we differentiate it again, then we will get the third line here by some rearrangement. And the Bernstein polynomial above are recovered if we substitute y equal to 1 over t. Therefore, one can prove that bnt1 is equal to 1, bntt is equal to t, and bntt squared is equal to n minus 1 over n t squared plus 1 over nt. And plugging all these expressions into the inequality and using the fact that t is smaller than or equal to 1, and we will get this inequality. And we know that as n gets greater and greater, then our expression here will get smaller and smaller. and that means that for all epsilon greater than 0, there exists a n naught such that 1 over n is smaller than epsilon as n is greater than or equal to n naught. Therefore, this expression here can be made infinitely small. And therefore, as the subnorm of the difference of them is smaller than epsilon, and that means the BNTF is the desired polynomial for the Weierstrass approximation theorem. And we are done with the proof of the Weierstrass approximation theorem. You may wonder why we need such a proof, if we know that we can use Fourier series to prove this. The difference between this proof and the proof for the Fourier series is that this proof provides a concrete way to construct this polynomial here. And that means if we are given an arbitrary f, we can immediately construct this polynomial. And this is very important because this polynomial here can be easily computed by a computer. And sometimes we want to make an approximation of a continuous function in the application, and therefore this proof provides a concrete way to construct a polynomial to approximate a continuous function. And we know that approximation is very important in a reality application. Although we have arrived at the same result as the proof in the Fourier series, this proof is even more important than proving the Weierstrass approximation theorem. So this is the end of the video about the proof of the Weierstrass approximation theorem using the Bernstein polynomial, and see you in the next video.